Let's say we have an undamped SDOF system, where its damping component does not contribute to the resistance against dynamic load. Assuming this system is subjected to external force, which its magnitude is a sine function of time and loading frequency. The system is said to be in forced vibration under this condition. The solution for x is the summation of complementary function and particular integral. The complementary function is the form of solution we use to solve for a SDOF system subjected to free vibration. Therefore, we may apply the simplified form of this function from previous video. The particular integral, on the other hand, is taken as a sine function of loading frequency and time, following the fashion of external force. Then, let's determine its partial derivatives with respect to time. Particular integral is a general solution for non-homogeneous differential equation, like the equilibrium equation we have here. Therefore, we just need to substitute the integral with its derivatives into the equation. From here, we may eliminate the trigonometric terms and further simplify the equation. Knowing the definition of natural frequency, we can further simplify the term k over m. After that, let beta be the ratio of loading frequency to the natural frequency of the system. We can now try to express the constant g in terms of other variables. Once we succeed, we can substitute it back to our particular integral. Then, recalling the solution x consists of complementary function and particular integral, we have now obtained the general form of that solution. You may have noticed that we still have two unknown constants, C1 and C2 remain unsolved. In fact, the value of these constants depends on the initial state of the system. Let's say the system is not at rest initially. Under this situation, we know when time t is 0, the displacement of system shall be the initial displacement. Same goes to the velocity. By establishing these two boundary conditions, we can solve for C1 and C2 that are valid for this situation. Through simplification, we will have the completed solution for x. If the system is initially at rest, we may just make the initial displacement and velocity of the completed solution of x 0. The resultant expression will be a valid solution for this at rest condition. From here, the term f over k equals to the static displacement of system. Meanwhile, the remaining terms on the right-hand side of the equation is a dynamic response ratio that helps us to determine the displacement response based on static displacement. What if the external force is a cosine function instead? The same process applies, with the exception where the particular integral should be in the form of cosine function as well. The following expressions will be the full solution of x for this. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.